Okay, so welcome everybody to another Ignition community meeting. We skipped the meeting last month because we had some internal issues and we couldn't make it, but it's good to be back again this month with another meeting. So as usual, we're going to start with some announcements, then we're going to have a couple of presentations, which we call the focus of the month. And then at the end, we'll go over some news related to Ignition and Gazebo. And at the end, the agenda is open if we still have time for anyone to bring up things that they want to talk about. This meeting is the first time that we have presenters from outside of Open Robotics. So far, all of our presentations have been from the core development team. So it's exciting to see people from outside and see what they're doing with Ignition Gazebo, with Gazebo Classic. So I'm looking forward to the presentations today. So let's jump right in with the announcements. We have a big one here, just one. It's about ROSCON that is coming back this year. Last year, if people remember, it didn't happen in like the in-person event. We only had a virtual event called ROS World, but this year ROSCON, the in-person is coming back. It's going to be in the end of October. The call for proposals is still open until the end of next week. And there's also a diversity scholarship for people who who qualify, who are from underrepresented groups in the ROS community. You may get a free ticket to go to ROSCON this year. So be sure to check it out and apply. If there are no other announcements, I'll just jump right into this month's focus with our first guest, Andre Ursula, who's going to be talking about deep reinforcement learning for robotic grasping from octrees using Ignition Gazebo. Are you ready to start, Andre?
Yes, I am. Thank you.
Okay, so I'll stop presenting and the floor is yours.
So hopefully you will be seeing my screen now. Yeah. So hello everyone, my name is Andre, and I'll present how I used Ignition Gazebo in my latest project to train reinforcement learning agents to perform robotic grasping. It is a project that I worked on during my master thesis at Aalborg University in Denmark. And on today's meeting, I'll focus on the aspects of using Ignition Gazebo within this project. But in case you have any questions, just feel free to ask. So starting off with the focus of my project, the objective that I was trying to solve was the task of robotic grasping and grasping of various different objects that can differ both in their appearance as well as shape. And I am focusing on vision-based robotic grasping, meaning there is a camera that perceives the scene. In my case, it's an RGBD camera. And the ultimate goal is then to grasp and lift these objects by the use of a robotic manipulator that has a mechanical gripper attached to it. So as the title indicates, I have decided to use reinforcement learning to approach this problem. And reinforcement learning can be described as a fancy way of solving sequential decision-making problems. But it doesn't require any large pre-labeled data sets as it is often needed for supervised learning. Instead, the agent collects data that it needs while it's training by interacting with the environment. So it does so by performing certain actions based on which the environment then returns some reward, which then tells the agent where those actions were good or not. And the goal is to maximize this reward, not only the immediate reward, but also the future reward. And with this approach, we can then learn a policy that will then help us estimate actions based on the current state. And in my particular project, I was looking into learning of end-to-end policy meaning that we directly want to map observations into some actions. So for observations, I have selected to use octrees. Normally, you would use either RGB or RGBD images for these sort of problems. But I wanted to see whether using 3D representation of the data is applicable and where there are some advantages to it. So that's why octrees. And these octrees are processed by a neural network. A large part of this neural network is 3D convolutional neural network that acts as a feature extractor. And at the end, we want to select actions in continuous space. And I have also selected actions that are in Cartesian space, which consist of the displacement of the gripper, as well as the yaw rotation and action for closing and opening the gripper. So this is the basic setup of what I was trying to achieve. And it's not only useful to have it working in the simulation or in Ignition Gazebo, we also in the end want to apply it on real robots. But I'll talk about it later. So, but how does one start with creating a reinforcement learning environment inside Ignition Gazebo? So for that, I can recommend using GymIgnition. It is a framework that provides interface for Ignition Gazebo. This includes Python interface, which makes it simpler to integrate with some of the popular deep learning and reinforcement learning frameworks. And GymIgnition also provides tooling for creation of the OpenAI gym environments, meaning that the environments that you create will follow this standard and be therefore compatible with other reinforcement learning frameworks that can implement reinforcement learning algorithms. This means that you don't actually need to implement the algorithms yourself. You can just use them from other frameworks. For example, in my case, I use Stable Baselines 3 for the implementation of actor critic algorithms. So if you want to build similar environments to what I'm going to present, definitely check out GymIgnition. Here is the link to the repository. They also include some examples that can help you get started. So once you start building the environment and defining the logic behind it, you will come to a point where you want to insert some models into the simulation. So where to find it? Again, for this, I'll just recommend using Ignition Fuel. It was discussed a few meetings ago. It's really nice. And in particular, I have decided to use the Google Scan Objects collection from Google Research, which contains more than 1,000 different objects, which are 3D scanned. Meaning that it can be used for many different things, but in my case, I use them for the robotic grasping. Once you start using them, you will soon find out that the SDF file of these objects and many other objects don't contain inertial properties, and so you'll need to estimate them. And from my experience, it works fine just to assume that the mass is uniformly distributed, and you just select some mass or randomly selected. For this particular collection, you'll also see that the mesh for each model has too much geometry to be used for physics. Some of these contain more than 50,000 triangles, which is just too many for the collision geometry. Therefore, you need to decimate it. You can do that manually if it's just for a few objects using Blender or something similar. But if you want to do it for all 1,000 objects, then having a programmatical approach is probably a good idea. Luckily, there are some open source libraries that you can just use. For example, Open3D or TriMesh that can do both of these. There are probably others. I just listed these two because those were the ones I used. So with these, you can pre-process the objects and then use them subsequently as data set in your simulation. So it's generally a good idea to split the data sets into training and testing, just to see what you have learned, what the policy can generalize to novel scenes. In addition to the objects I have described, I have also used a number of random textures just to give the scene more variety. And I apply this to the ground plane of the environment. Obviously, you also need some robots. I have decided to use Frank Panda and UR5, but you can use whatever you want. So having these models, you can imagine that these are some of the examples of the environment that can be used. So these are just snapshots at the beginning of each episode of many different episodes. And we don't do this variety just to make the task more difficult or something. It is something that within reinforcement learning is called domain randomization. And it is done in order to simplify the transfer from simulation to real world. So we do this in hope that the policy that is learned will be more general and hopefully encompass some of the real world scenarios. But it doesn't need to be only visual randomization. You can also randomize physics and other things. So in my case, I also randomize the scale, mass, and friction of objects, which are spawned randomly in the environment. You can also use random configuration of the robot joints at the beginning of each episode. And in my case, I have also randomized the pose of the camera because I have 3D observations and I wanted the policy to be invariant to the camera pose. And that was again done with the hope that then in real world, I can just place the camera wherever it fits the real world, and I don't need to replicate exactly the position and orientation as it was in the simulation. Obviously, on top of that, you can add some sensory noise just to make the readings more realistic. So on the right, here are some examples of what the observations could look like. So we have RGB image, depth map, and the resulting point cloud. And there are also coordinate frames indicated for the robot base and the vector of the robot, as well as the camera. So with this, now we have an environment that can be used to train agents. And the training itself will largely depend on what algorithm you select, how much you tune hyperparameters, and so on. But it can look something like this. So here are 3 videos at 3 different points in the training. So one at the very beginning, one after 100 episodes, and one after 1,000 episodes. And there is definitely some progression going there. So at the beginning, the actions are very random. It doesn't even try to approach the table. But after 100 episodes, it figures out that it can get reward only when it actually tries to approach the ground plane. After 1,000 episodes, it figures out that it's probably a good idea for the objects to be between fingers. But at this point, it's still not able to time the grasp action properly with the placement of the gripper. But eventually, after many more episodes, it can learn a policy that is capable of grasping some of the objects. So here is an example of doing that on Frank Panda. And as we can see, it can grasp some of the objects. Sometimes it takes it longer in its multiple trials to do it, but it can grasp majority of the objects. And so this particular case, the agent was trained for 500,000 episodes, time steps, which means each time step in this case is one occasion on which the agent selected an action, received reward, and acquired new observation. And those 500,000 time steps, on my machine, it takes approximately 3 days to train. So just to give an idea of how long some of these problems can take to learn. Similarly, the same environment as well as algorithm can be applied to different robots. So in this case, the UR5. And Yeah, so it can be applied as it is, just on different robot, because both the observation space and action space is invariant to the robot model. I should maybe mention here that for the motion planning, I am actually using MoveIt2 to generate the motions in the Cartesian space. And that's another nice thing, because it provides this level of abstraction on for the action space that is invariant to the robot you use. And those details are just handled by whatever URDF model or URDF description and robot model you use. Yes, but as I said at the beginning, the ultimate goal is to transfer it from the simulation to real world. And so this is the first attempt I tried to doing that, one of the first agents that I trained. And as you can see, so the policy is not very deterministic. It still does some random actions, but eventually it's able to grasp some of the objects. From the experiments, the success rate for real world is approximately 68%. However, in the simulation, it's a bit more, so it's in the range of 80% or more for some of the agents. But that could obviously be improved just with longer training or having better observation with a higher resolution and so on. One thing I should point out here that due to this undeterministic behavior, there is not really any guarantees of safety. So I wouldn't really trust to leave it unattended with rigid objects. So that's something that will need to be addressed, and just incorporate some safety into it, probably with some traditional approach or yeah, something. And so I'll close this with just mentions of the repository, as well as examples that you can run in case you want to try it out. So this is the link to the repository. It contains more information about different things that I might not have mentioned in this presentation. It also includes instructions of how you can install it and build it and use it. But I should point out that the local installation can be a bit cumbersome just because of the number of dependencies. That's why there is Dockerfile that you can either build yourself, or you can just pull one of the pre-built Docker files from Docker Hub and then use it to try the examples. So here are two examples, but there are others that you can use. So one is to evaluate one of the agents that I have already trained, and the second one allows you to train your own agents if you want. There is a small batch script that spins up the Docker container and also set up the make it possible to see the graphical interface and other things. You can also load your different data sets if you want. And then you can launch the example, which then will use one of the pre-trained agents I have already trained. You can select one of you, and it will open something like this with both the graphical client for the Ignition Gazebo, as well as RVs2 with the point cloud observation and the coordinate frames. You can also train your own agents if you want. You can change different hyperparameters, you can try different algorithms, change the environment, reward function, so on. Similarly, just a different example. I should point out that this can take some time. This can take a few days before you reach something meaningful, so plan ahead. And that also leads to the repository. So there is a lot of optimization that could be done. I'll just mention one, which is currently there is no support for parallelized environments, meaning that it's only one environment you can use at a time to collect data and train. However, it would be nice to have the ability to use multiple environments simultaneously to collect data, which would also give more variety to the data itself. And also make it more scalable, so you can run it then on server with multiple cores, or even on multiple different machines simultaneously. But that's something I have not looked into yet, but maybe will in the future. Yes, so thank you very much for listening. I hope that I'll see in the future more reinforcement learning projects using Ignition Gazebo. Thank you. Thank you.
Nice. Thank you, Andre. That was very nice. Lots of cool GIFs and nice images there. Do people have questions for Andre?
I have a question. So I may have missed this, but what was your reward function?
Yes, so in my case, I used a composite reward just to make it faster to train. So it consists of multiple different things, including first approaching the object, then touching it, then actually grasping it with both fingers, and then lifting it above certain height. But I also included a negative reward for collision with the table. That's something we don't want to have. And also just some fixed small negative reward at each time step to make the agent act more quickly, to incentivize it to perform the task as fast as possible.
I see. And then when you did the simulation to real world, did you only use the policy, or did you have to do additional training so that it works well in the real world, or did you what were your difficulties with that?
There was no retraining in the real world, so it was just trained in simulation and then directly transferred to the real robot using exactly the same thing. The only difference was the controller for the robot, more or less, and use of physical camera to acquire the data instead of ignition rendering.
Okay, thank you.
I have a question. So as you presented your results, you said that in simulation you had approximately 80% plus accuracies, and then in real world you got a par 70%, as you said, like close to 70%, right? So I was really wondering, like in simulation, most of the time, like we really expect like 100%, right? So at least for like like that becomes a challenge in all kind of simulation kind of research, right? The data set is not good enough anymore after a certain period of time. We're really good at like grinding the data. So what are the things that you found that made you feel like at 80% you're pretty good with your simulation work?
Well, I wouldn't call it really good. It's definitely not. It's far from state of the art. But I was also aiming to provide more generalized solution, let's say, and it's also end-to-end approach, whereas some of the more robust solution would use graph synthesis instead of the full control. So yeah, those 80%, it's definitely not the most that can be achieved on those objects within the simulation. It's just what I had time for, let's say, to train. Obviously, it would be much nicer to have it trained for longer, but I only gave 3 days for each of the agents. Yes, so if you have more agent, it can take a few more days.
Yeah, thanks, Andres. Yeah, nice presentation. Thank you very much.
Thank you.
Yeah, I have a question. Thank you, Andre, for that wonderful presentation. I just wanted to know if have you considered any sort of sensor fusion approach to this, in terms of maybe taking a feedback based on force or torque, based on the rigidity of materials. Is it possible to go ahead and fuse so that hopefully it gets better at the whole grasping setup?
Yes, so I have a setup where I can include proprioceptive observation, whatever you want. I set it up for the gripper position and orientation. But when I was running my experiments, there was really no noticeable difference in the success rate between those two. It was only like 2% on all scenes, which wasn't really, I would say it's not really worth the effort of going there. But it might be a good idea if you want to include the forces and torques, as you mentioned. especially if you have some sensitive objects and so on. I was really just focusing on rigid objects, and I wasn't really worried about breaking.
Right. Okay. Thank you.
I have a question. Hi, Andre. Thanks for that presentation. I just wanted to ask you that based on the grasping policy which your robot has learned, if you change the orientation of any object in real world, and if, for example, if that object is not something on which the robot was trained, so it's unseen object. So can your robot pick it while training it in the real world?
Yeah, so all of these objects were previously unseen, and actually also these objects, these are all novel scenes. So as I shown here, I have separated the data set for training and testing. So this was used to actually evaluate the agents, and those were the 80% or whatever it can achieve. And similarly, in real world, I didn't really have any objects in real world that would resemble the objects from the simulation. It was just some random objects that I had in my hand.
So there is, sorry, one more part. There is the can which can be seen. So if I keep the can in perpendicular direction, or if I change its orientation, can I assume that the wrist or the end effector is also going to change its orientation according to the object?
So changing the camera position is the question?
No, what I mean is, if you change the orientation of an object, if you keep it upside down, because it can be seen in the video, it can be seen that it is kept in horizontal direction. So if you change the direction of the can vertically, will the wrist also, will the end effector also change according to the can?
It should, but I don't think I had success with the can standing upright. It's just more difficult, and I also wanted it to be more safe. So if it was upright, it would be more structurally rigid, and that could be some damage if the robot hit it from top down. So that's why I just let it lay down.
Okay, thank you.
But it should be able to generalize, at least according to the result in the simulation, because the objects are spawned randomly. Obviously, there is some bias when I am placing the objects there. I don't place them in a way where it could damage the robot.
Okay, understood. Thank you.
Andre, on slide 7, you show the objects that you used for training and for testing. Is this all of them? Because I don't think that uses the entire Google set, right? Like, how did you choose these models?
So this is not all of them. I did not use all of them because there is currently so the assets for both the mesh and texture within Ignition are currently kept within RAM and VRAM, which means that I would run out of memory if I try to use all of the objects, which is why I have just selected 80 and 20. So 80 for training, 20 for testing. I should also point out that some of these objects are not very, they will need to be processed more, let's say. So for example, this one, it consists of 2 disconnected objects, but since it is designed as a single link, they will be rigidly connected. So yeah, some of these objects also need to be, let's say, blacklisted for certain applications. You cannot just use all of them. Yes, but how have I selected this? I just aimed for the ones that were single object and that had some variety in them. And also some of these objects, many of them are either boxes or shoes or similar objects. And I didn't want just majority of my data sets to be just boxes and shoes. So I also aimed to not only have different visual appearance, but also the shape.
Very cool.
Yes, as a note, I think the issue with the RAM at the VRAM, I think it's solved in Fortress. So yeah.
That's great. Thank you.
Cool. Thank you, Andre. Another round of applause. Thank you for the presentation. That was very good. We can go to our next presentation, which is going to be by Chris Burns. Let's see. Oh, I lost my window here. Chris, are you there? Are you able to share your screen?
I'm here. Can you hear me okay?
Yes, Chris. Yeah, we can hear you. So Chris is going to be presenting about the JPL Open Source Rover Challenge by AWS that was done with Gazebo Classic. So Chris, you have the stage.
All right, thank you. I didn't think ahead. I'm on a high-res monitor, so let me see what this looks like when I try to share my screen. If I can remember how to share my screen on Google.
There's a box with an arrow in the bottom.
I see, right here. Okay.
That looks good to me.
Let me try to see what it looks like if I, no, that's not going to work. Okay, so I'm going to just share like this. Don't peek at the upcoming slides. Just listen to me when I'm talking. So thank you very much for giving me the time to talk today. I'm here with Jeremy Wallace, who is our senior principal RoboMaker SA, and I think we're going to tag team this a little bit. What I'll do is I'll talk about the challenge initially, and I think he has some things that he wants to talk about. So this is actually kind of old now. This December 2nd to February 21st date you see here was 2020. So this is 18 months old. In AWS years, that's like 40 years. I was a young man when I started at AWS a couple years ago. And now you can see what it's done to me. So the purpose of this challenge was really to socialize the open source rover. We teamed up with JPL, who's a great partner of AWS, and we wanted to get their open source rover some love and attention. So we hatched some ideas to make it a contest to get the word out, to get them, because this open source rover is a real thing. You can go to GitHub, you can find the plans for this. It's very, very popular in some colleges, some high schools. And so again, it's the goal here was to socialize that and at the same time showcase some AWS services. So what the challenge was, we had a simulated Martian environment in Gazebo. We had a robot, open source rover that existed as a URDF file. So we had all the makings of a ROS package. And the challenge was to get the rover to start from its landing zone to a particular point on this Martian surface with as little damage to the rover as possible, actually no damage to the rover as possible. And it was to get it there in the fewest amount of time steps. So we used reinforcement learning, a couple of technologies I'll get into in a minute. But I wanted to just make sure that we understand that the challenge was relatively simple in principle. Get the rover from point A to point B using only reinforcement learning. You couldn't use any other type of algorithm. And we controlled that pretty tightly by just allowing participants to edit the reward function of the code that we distributed. So I should have been showing this slide when I was talking about that, but essentially you see here, it's a little bit hard to see. The rover is over here on the right. He starts at 0, 0, and he had to get to this circle over here. So 44.25 meters in the negative x-axis and about -4 meters in the y-axis. So this Martian surface you see was created in Gazebo, and I'll dig into those details here in a minute. So just to recap on the challenge, the way an episode ended was if you either, by the way, Mars was flat in this challenge. So if you drove off the side of Mars, your challenge ended, of course. If your rover hit something from the side, anything on the side, the episode ended. NASA and JPL wanted to put some actual principles in place that they have to be super careful with their rovers when they're on another planet. You can't just run over stuff. So I mean, if one of the challenge features was we put IMUs on this rover, and on the Z-axis I would measure how much jerk or how much impact the Z-axis took. So if you go over a really bumpy rock and you just bottom out the rover like hitting a pothole in your car, that took points away from your ultimate goal. And again, I'm talking over myself here. So if the rover hit anything other than rolling over it with its wheels, that ended your episode and you had to start over. And you also had enough battery life for 2,000 time steps. So the purpose of this challenge was So this was wrapped in a ROS application, as I had mentioned, and there were three primary components. There was the Rover, which existed as a URDF file. That was the Rover. I think Jeremy did some work on that. I don't know if we got that from JPL or what, but that was some, the URDF file was relatively accurate. We had few minor tweaks to that. Then there was the simulated world, which existed in Gazebo. That was a Martian surface that I created, and I'll go over that in another moment. And then there was the RL agent. So that's all the complementary code that ran with this that ROS would run in RoboMaker to create the episodic reinforcement learning and then deep learning training. So I'll go over these one by one relatively quickly. As I mentioned, so on the left here is the open source Rover. This is a kit that you can assemble yourself for, I think it's about $2,000 US, maybe a little bit more. But it's a fantastic model for robotics. It's Raspberry Pi controlled. I think we upgraded ours to Xavier, NVIDIA Xavier controlled. But lots of features on it, lots of great opportunities to practice robotics and learn about robotics at the high school or the junior college level. And on the right was our URDF file. So very, very accurate as far as I was concerned. The physics were pretty much accurate. We had to use Martian gravity, Martian temperature, a lot of fun experimenting with that to get that correct. And as I mentioned, this exists as a URDF file. So it had a camera, it had several IMU sensors on the wheels to detect speed. We kept the challenge relatively locked down. I struggled creating the challenge. I struggled with making it too hard or making it too easy. I was worried if I made it too hard, nobody would have any fun and it would be a black eye. But if I made it too easy, then I was worried we'd have 5, 6, 20 winners and there was actual cash prize. I forget how much it was, but it was not a trivial amount. I think it was 20 grand, something like that. So I struggled with that. So some of the things we did was I controlled the motion of the rover to only forward and left and right. So you couldn't go backwards, you couldn't change speeds. And then now the simulated Mars surface, listening to the first caller for the first presentation, I wish I would have had some of his tools in his toolbox before I started this challenge, because what I started with was some internet pictures of Mars, a few textures, and then many, many hours learning MeshLab, Blender, and Mesh. And I'm sorry, that's Autodesk's I forget, Mesh Mix, MeshLab, and Blender. And what I would do is I would create a 3D rendering as close as I could to one of these pictures, and then I would add the textures with Blender. Then I go into Mesh Mix and decimate. He had mentioned about the number of polygons in some of the models. Some of the models I was creating had hundreds of thousands of polygons, and Gazebo, it just wasn't having it. So I had to work with that and decimate that down to get to the point where the Martian surface was navigable, but also loadable in RoboMaker. And in I didn't want to require a fleet of compute just to run one simulation. This existed as a world file. This was it was a fun experience putting this together and learning about this. So you start with the default, and you can see here we have the gravity, the Martian gravity here, and we tried to put some Martian temperatures in there. It had very little bearing on the challenge, admittedly, but when you're talking about actual fluid dynamics and mechatronics, Martian surface temperatures vary drastically from Earth. So that's something that would be interesting for a future challenge. So let me get into the RL agent component of this. I just summarize it as the RL agent. There's many components to that. I use RL Coach from our friends at Intel, and RL Coach is a framework. It has some similarities to baselines, like the previous presenter had mentioned. And what it did was it allowed me to implement this clip PPO algorithm relatively easy. That's a proximal policy optimization. So in reinforcement learning, this was a continuous action environment. So the rover continues to move. It doesn't, even though it takes an observation after each time step, it's constantly moving. So the PPO was probably the best option, I thought, for the challenge. And I limited participants to that algorithm just for that reason. I didn't want to give, again, too much complexity. I use OpenAI Gym, of course. So the Mars environment existed as a Gazebo world file, but it also exists as a environment in OpenAI Gym, where the reward function lived, where all the sensor data was coming in, telemetry from ROS. And then finally, this all passed TensorFlow for the deep learning aspects of the. Basically, it was it was image processing. The camera on the rover was the primary source of input for training. I tried to do some sensor fusion. I know somebody had mentioned about that because I wanted to get IMUs in there. I wanted to get a couple other aspects in there about time steps and battery life. Very, very complex to put into a challenge that would easily translate to something that somebody without a lot of RL experience could conduct. So we limited that. And so then the reward function, as I mentioned, this is the function we allow the participants to completely rewrite this function. Funny story, I had, when I built the simulation, I of course had to solve it. So I ran many simulations, many iterations of the reward function. And so the working model that I had, the story is, so December 2nd, we're at reInvent. I'm going to be on TV with JPL Labs to announce this challenge. And it wasn't done. It wasn't done on December 1st at about 1 a.m., which was technically December 2nd. I actually finished the code on the bus to the exhibit hall where we're going to announce, and I pushed it to get from the bus on my hotspot, and I accidentally pushed the solved reward function along with the code. So what ended up happening was I gave the participants a solution, but they still had to refine that. So it was still a challenge. It was still a contest. They had to take my very, very basic solution and then refine it down to a winning entry. And went backwards, I apologize. And then, as I mentioned, this was all wrapped in ROS. So what ROS gave us was the capability to the repeatability. So the repeatability is the key in reinforcement learning. When this was wrapped in ROS, that means RoboMaker could run it and run it and run it and run it. And you had the tools like RViz, a couple other things I think Jeremy wants to show. And so the RL agent, the Rover, and Mars all rolled into this ROS application is what gave us the ability to release this as a challenge to the public. And I think, Jeremy, those are the only slides I have. I'll let you chime in here. Otherwise, I could talk about this for for the rest of the day.
We can hear you, Jeremy. I see your mouth moving, but I see you're unmuted, but while Jeremy figures out his setup, how about people ask Chris some questions?
Yeah, it's a perfect pause, and I can take some questions.
I don't know if this is coming up. I don't want any spoilers, but like, were there winners? How many winners? How was the result of the competition?
So we announced this. We took entries until the end of February 2020, and we had a winner. It was a young. As a matter of fact, he had just wrapped up college in Australia. Jordan Gleason was his name. He had the winning entry, and we actually still have, and it's still live. Let me verify. I'm kind of stepping on Jeremy's toes. I'm sure this is some of the stuff that he wanted to talk about, but I'm trying to find the URL. Spacechallenge.tech, maybe. Yes. So I'll drop this in the chat window here. That's the website that we used at launch, and there's a link here to the leaderboard. I'm trying to remember where the link is, and you can actually see the winning. You can see the winning. So I can't talk and browse at the same time. The winning submissions, you can replay those. And there's some funny ones in there where rovers went off the edge of the world. What I did was I took so this. I see you, Jeremy. Did you get your mic fixed? Not yet. Yeah, so what I did was I actually started with some STL files from NASA's website, and there's one called the Curiosity Path landing zone. It's just a big square, and I enlarged that for the Gazebo environment, and that's where I ended up with a couple 100,000 polygons. And so I had to begin the decimation process. And every time I put rocks in, I was trying to go for real high fidelity or high definition just because of the cool factor. And what I was doing was I was just putting far too much data in there for the physics engines to handle. So I had to continually scale it back until I got to a point where I felt like it wasn't quite cartoonish, but it also wasn't, it wasn't too much data for the physics engine to handle. Because the whole point of it's hard to tell from the slide. I'm still sharing here. It's hard to tell from this image, but if you look closely, you'll see the polygons. There was no flat surface. Nothing was smooth. And what happened was, when the rover navigates, these black boulders here, these lava rocks and these like granite rocks. Oh, is that you, Jeremy?
Hey, can you guys hear me now?
Yeah, it is you. Yeah. So I'll just
okay.
Let me pause because this has been I just been black belting this, and I wanted to let them hear what you have to say.
Sorry about that. I don't know. I'm just gonna put in these earphones. All right. So can everybody hear me still? Yeah. Cool. So here I'll just I know that we're kind of maybe a minute over. I'll just quickly just show you guys what it would look like for these developers to connect and run these simulations in the cloud. If you can imagine with AWS, you have access to compute of all different sizes, so things like GPU, CPU, and so with RoboMaker, you can run your rock and Gazebo-based simulations in the cloud really easily. So here I'm just going to share my screen. Okay, can people see this screen now? So in RoboMaker, we have these development environments. It just takes a minute to go and create one. And then once you have one up and running, it's got ROS already pre-baked on it. And then you have access to a virtual desktop that will actually stream those pixels over the cloud to you as a developer. So what I have here is these two windows open. And they're running a Gazebo simulation as we speak. Here, let me just open them up. Sometimes, there you go. Okay, so here's Chris's Martian world that he created. And so this is an actual live Gazebo simulation up and running in the cloud. And then on the right, we can use the teleop command to move this open source rover, which is really meant for terrestrial environments, but we've brought it to Mars here to run the reinforcement learning agent that Chris was talking about in simulation. So it's something that just takes a minute for developers to get started with. It took me about 10 minutes to set up Chris's whole sample app in AWS. So if you guys want to try it, feel free to dive in. The other cool thing, I don't know, you can have multiple screens in the virtual desktop. So you'll notice I can just kind of drag. Here's my second window. I can drag things across. And this entire thing's running in the cloud. So that means it's not on your local machine. You can share the configuration with the other teammates. They can just connect and resume the simulation as you left it. So interesting set of tools. If you want, give it a try. If you have any questions, absolutely reach out. We're here to help and here to help you use RoboMaker. So that's all I have.
Oh, thank you, guys. Do we have more questions for them?
Yeah, out of curiosity, my experience with running competitions has usually resulted in teams doing weird things or pushing the limits of what the rules or intent were. So I'm kind of curious if you experienced any of that. Like,
absolutely, yeah, absolutely. I had submissions that that didn't use anything that they were supposed to use. Fortunately, I had anticipated some of that, and we had clearly defined the rules. There's code comments throughout the entire Git repo that says if you change this, it doesn't count. If you change this, it doesn't count. And then the submission, the way they submitted it, it had to work with the original construct, the original engine. So if I dropped it in, it didn't work in any way whatsoever, that means that they changed something other than the reward function. And I just had to tell them, look, you've changed something, go back and do it again without changing those things. So, I mean, when we envisioned it, I really wanted to allow multiple algorithms, not just the PPO. I wanted to allow them. So I wanted to say, hey, if you don't want to use TensorFlow, you want to use PyTorch or MXNet or some other, go ahead. But the problem was that, it was a small team that put this challenge together, and we had to build an automated, mechanism to grade. There was hundreds and hundreds of submissions, thousands of entries. So we simply couldn't build something in a short amount of time to allow those different changes.
Yeah. Do you know if everyone tried and tested on RoboMaker, or did you give teams time on RoboMaker to validate their solution?
Yeah. So everybody that entered got like a $250 credit on AWS, and then the winner got I don't remember the exact amount. Do you remember, Jeremy? Was it 20K? And second place got 10K or something like that? Yeah. So I'm gonna do my lip reading. I think Jeremy said yes, 20K and 10K.
It's 25. Okay. I got multiple mutes here, so sorry about that.
Sorry.
I have a quick question. Looking into the website, it looks like you can pre-register for the next year. So do you have plans to repeat competition?
Yeah. I think there's always plans. How mature those plans are is probably the question that you want to ask. And right now, I don't know that we have anything concrete planned. But I've almost recovered. It's been about 18 months. I've almost recovered from the first one, so I'm getting ready to do another one. And this time, I think I want to go further out. I'm thinking Europa and maybe some subterranean submarines and rockets to get there. And I think I'm going to raise the bar on this. And but when we do that is remains to be seen.
Did you guys try running the train models in the physical rover?
No, we did not. We didn't have a Mars handy to run them, but and also I'm just being silly. We didn't have unlike the first presenter, we didn't have a clean translation from a robotic arm to simulation. So we didn't have the facilities to take this code and put it on the rover. We actually had plans to do that at Remars in 2020, but of course Remars was canceled, so that work unfortunately ended prematurely.
Yeah, one thing we do have, there was a very interesting reInvent presentation when we launched RoboMaker with Nick from JPL. Showed an actual real open source rover and then a digital twin running in the cloud. So I'll send over the link if you guys are interested.
Cool, thanks. Any other questions for them? Okay, another round of applause. Thank you guys, that was very fun.
Thank you. Thank you for the time.
Yeah, looking forward to the next challenge.
I'll make sure we announce here when we come up with another one.
Yeah, for sure. You guys are always welcome here. Thank you. Let's see. Let me share my screen again just to go over the news that we have very quickly. So these are some links that Kat got together for us. So just some things that people may be interested in. RoboGym, so very related to everything that we're talking about here, was released recently, like May 20th. So it's like a month ago. It's also for reinforcement learning of robots using Gazebo Classic. So people check it out if you're interested in it. Yeah, also like Open Robotics is welcoming GSOC students that, we're participating in GSOC again this year. So we have a few students contributing to Ignition and to ROS with documentation, with code. So we're very happy to have these students here participating with us. There's this great ROS2 and Gazebo tutorial. If you're looking for a nice introduction tutorial, this is a very detailed, nice one that you can check out. Very well organized. And finally, this one, I don't know if Carlos has more information, but the virtual robotics competition is announced for 2022. So that's coming up. I don't know if you have anything to add, Carlos.
Well, so I think if I remember correctly, the requirements is that you need to be affiliated with a university. But other than that, if you're interested, like with marine simulations, it's gonna be very interesting. It should be very cheap or even free, and it's gonna be using Gazebo Classic as well.
Cool, very cool. And that's it for the news. So we have only 4 minutes left. So let's see if we can cover the two agenda items that we have down here. Who was the one who put down robot grasping? Speak up.
Yeah, it's me. As Andre has mentioned earlier that I mean, first I have to say it's a wonderful project. I just wanted to ask him sort of a question that how can we extend this project for soft bodies and perishable objects? Because this seems to have been ignored for a long time, that Ignition Gazebo has some robots which can do all these grasping problems, but when it comes to soft bodies and perishable objects, there's no other framework available online. So
Andre, I don't know if you...
Yeah, I can add to that I think that's largely influenced by what physics engine is available. And yeah, obviously then the performance for soft bodies would be lower, I would assume. But I haven't done any research on that part.
Okay, thanks.
Yeah, there are other people here, like maybe Adis or Steve can talk more about the soft body support, but we recently added Bullet support. There was also a community meeting about this, and Bullet itself has some soft body support. We haven't added that to Ignition Physics yet, but you know, there's a path there to possibly add that in the future to train this kind of stuff. When you say perishable, you mean like objects that break apart and collapse?
Yes, ma'am.
Yeah, we have support for like breakable joints, which is a very inconvenient way of modeling that kind of behavior. But yes, like the cool thing with Ignition Physics is that people can integrate any physics engines that have support for this kind of phenomena and start using that in Ignition Gazebo. I don't know if any of the physics guys want to add anything. Doesn't look like it. Or
no issues. Thank you, ma'am.
Yeah. Both Bullet and Dart have soft body, but there's quite a bit of work needed to get that integrated into Ignition Physics and Ignition Gazebo. We welcome any PRs. Help is definitely very welcome.
Yeah, and I'll add that if you think it's you know, tricky to come up with inertial parameters, you know, there's only 6 of those, or you know, there's a relatively small number of those compared to how many parameters you have in a soft body model. So I think you know, even once we get even if once we had it integrated, it would be pretty challenging to choose all the parameters in a reasonable way. So not easy.
Well, before we run out of time, let's go to the next agenda item. Who was the person who added this?
That's me. So if I can share my screen, it's
Go ahead.
So with I'm from Picnic Robotics. We have been collaborating with Hello Robot. They have a nice robot called Stretch. The one here. It has very nice little manipulator. It's a mobile base with diff drive. It has a telescopic arm with a lift. And we have been working with them to. This robot also works in real life at Rostron Galactic. And also we have been integrating it with Ignition as well. With also Movie 2. Apart from Andre's work, we have a kind of control server, control action server that also enables us to control it via the where the RViz interface will move it. So we can plan and execute, and we can see that the robot can actually move. So I just wanted to share with the community that we have been working something like this. And also, we have planners for mobile ways, so we can plan them together actually. So like we can plan the robot, the arm, the gripper, everything together, and it will plan accordingly. So like this robot does not have like lateral axes in the arm, but instead it uses its base to move on the lateral axis using the depth-wire planning. So we can just command plan and execute, and it will turn and will sting on ignition as well. So also as a part of the project, we also ported the AWS RoboMaker small house role to ignition. I hopefully send the PR to them soon. And so now we also have the world working on ignition with the objects slightly changed so that we can grab them actually rather than them being static objects. So that just want to share our progress, and maybe someone will find it cool.
This is really awesome, Vatan. You should come back another day to take like, the entire meeting to show us what you've done and teach people how to use it. Let's talk about it afterwards. Unfortunately, today
sure.
we're kind of over time already, so I don't want to keep people here longer than promised. So yeah, but thank you everybody who joined. Thank you everybody who presented. This was a very nice meeting. Nice to see everybody again. And we're gonna be back again next month. We haven't decided the topic yet. If you want to present, feel free to email us, contact us. I'm Louise at openrobotics.org. Just feel free to email me directly. And be sure to submit proposals to ROSCON. It's closing next week. Sounds good? See you all. Bye-bye.